All right, guys. So here we go. We're going to go ahead and dive in. Again, singers that were taking the photo, you can do your do now later, but we're going to go through log expressions. In log expressions, we're going to start off with a little bit of review knowledge. So stuff from first semester and stuff from Algebra 2 that should be retained. And then we'll build off from there. So if I'm going too fast, let me know. If I'm going too slow, let me know. And we'll keep it pushing. All right. Okay. So up first, what do we know about log expressions? Okay, well, we know that a log expression is written in the form of log base b of n, right? We should be comfortable with that. That there we go. We should be comfortable with that, correct? Log base b of n, and it's equal to or represents the value that base b must be exponentially raised to in order for to get that value of n, correct? That's what log is. Log is tying it to an exponential. Okay. Um, if you look at the table here, these are our basic properties of log. So up first, we have our um uh log one rule, like rule of one. So the log of any base of one is going to always be zero. Okay. That's because any base to the zero power equals one. Do you remember that? Okay. So our rule with one, then we have log base b of b. If you're taking the log and the argument and the base are the same, it's going to equal one. All right. That's the identity property. If I'm taking the log, and the base and the argument are the same, it's going to equal one. Here, if I'm taking the log and the base of the log and the base of the argument are the same, then the solution is going to be the power. Do we see that? Yeah. Yes. So if I had log base 2 to the x, the answer is going to be x. Okay. It takes the whatever the power is. Okay. Here again, the inverse property. If I have an exponent raised to the log of the same base, they're inverses of each other. They cancel out. So it's just going to be, remember the inverse properties? Okay. Here, natural log. Natural log has the exact same properties, but instead of using log and b, it's ln and e, right? Natural log of 1 equals 0. Natural log of e equals 1. It's the identity. They are inverses of each other. Same thing here. Natural log of e is going to be whatever the power is going to be the solution. E raised to the natural log is going to be just the argument, is going to be the solution. Okay. That's because they are inversely related, log and exponentials, correct? Yes? All right. If we did not leave first semester knowing that, I'm sorry. I did something terribly wrong. All right. But I didn't because we know that. All right. So up first, we talked about in Algebra 2, converting from log to exponential. Okay. Converting from a log to an exponential. What we're doing is just simply saying, what is the log asking us, right? And so the log is asking us, it's your base to your solution equals the argument, right? So the base here is 2. 2 to the third power equals 8. Correct. True statement, right? That's all the log is saying. Yeah. So let's try it again. This is saying 3 to the half power equals the square root of 3. This is saying 5 to the negative 2 equals 1 over 25. Remember, negative power doesn't mean you have a negative solution. It means that it belongs in the denominator. Okay. This is using common log, which means that your base is automatically what? What's my base? 10. Common log means your base is automatically 10. So therefore, this is saying 10 to the power of 1 equals 10. And then this is your log rule. So we have 6 raised to the log base of 611 equals 11. And this is just simply saying log 611 equals log base 611. They're the same, they're equivalent. Okay, so that's what it means when we're going from log to exponential. Now let's go vice versa. So exponential to log. So how can I write A as a log? Your base stays the base. There we go. Your base is going to stay your base. So it's going to be log base 4. Your solution becomes your argument equals the power. Do we see that? Your base is going to stay your base. Your solution becomes your argument. Your power becomes the solution of the log. Okay, so let's try it again. On B, what does that look like? There we go. There we go. Okay, on C, what does that look like? There we go. Okay, and then D, what does that look like? There we go. I was about to write equal first, and I had to transform that equal into an 8. Magic. No, I just do it because it makes my heart feel better. Sometimes my numbers merge, and I want to make sure you can clearly see that they're separate. All right, these skills are helpful because we have to be able to solve. And once we start solving, we need to remember these basic concepts that when we're solving and evaluating. Okay. How do you feel? Is this ringing bells? You're like, I've done this before. Okay. All right. So what I want you to do, you're going to do example 3, and you're going to practice converting from log to exponential quickly, and then we'll keep going. All right. So quickly do these. All right. So really quick, what's my exponential here? Perfect. 5 to the power of 3 equals 125 on B. Why can I write? What is wrong with me right now? I got it. All right. C. 1/2 to the power of the negative 6 equals 64. 1/2 to the power of 6 equals 64. All right. And then D. All right. So we're pros, right? Yes. Yes. Now we are. All right. Let's keep it going. So here we're talking about common log base. So when we have common log base, we are working with the 10, base of powers of 10. And this is going to be important when we get to our log plotting because it's based off powers of 10. So as we keep moving through this unit, you're like, oh, okay, that's what this means. That's helpful. Cool, cool, cool. So logs of base of 10, again, that's our common log. Okay. So when you're evaluating the common log, you're simply asking yourself, 10 to what power equals this, right? How can 10 to what power equals 100? That's all you're asking yourself when you're looking at common log. Okay. Does that make sense? So when you're looking at common log, you're saying self, 10 to what power equals the argument. All right. So this one would be 2 because 10 squared equals 100. Agree? All right. 10 to what power equals the square root of 10? 1/2. Good job, Josephine. It would be 10 to the half equals the square root of 10. Mhm. If I have a half power, that means I'm taking the root of it, square root of it. All right. 10 to what power equals 1 over 1,000? If it's a fraction, what does my power have to be? A negative. So 10 to some negative. Perfect. 3. How many zeros are there? 3. That's how you know it's 10 to the negative 3 equals 1 over 1,000. Do we see that? All right. This is a combination. If I have log base 6 of 6, what does that simplify down to? 1. So 10 to the 1 equals what? Log base. Remember, if the base and the argument are the same, it's just going to equal 1, which is why this became a 1. And 10 to the 1 is just 10. Okay? Yes? Do we see that on the other side as our rules? All right. So the reason why we're doing this is because these things would be on non-calculator, which means that you would have to know the rules and know how to manipulate the rules. Okay. These were questions that would be on non-calculator. So you would not have the backup of typing it into Desmos or typing it into the TA84. You would need to know the rule because it's on the non-calculator section. Got it? All right. So I know it sounds like I'm driving it in, but it's because it's not, you won't have any other option but to know it. All right. Now, what I'm going to show you are examples of what would be on calculator. These are the type of problems that would be on the calculator. If I had log of 34.5, or if I had the log of 4300ths, or the log of -3, these would be on the calculator section of the test. Okay? Because these are not ones that you can easily manipulate or figure out. Does that make sense? So we see the difference between the two? Okay, so just really quick, I'm going to open up Sylvie. Hey, girl, hey, where are you? There she is. I'm going to clear. Okay. When you're doing common log, you just press the log button. You don't have to change anything. Press log, type in. And remember, our magic number of rounding is to the third decimal place. My calculator is already set to round to the third decimal place, which is why I just showed up. They said it's a good idea to teach you guys around to 4 decimal places, but they're only going to be looking for 3. So we're just going to practice 3 if that's okay with y'all. If it asks you for the 10,000ths, then I would hope to know that you can move over one more. Okay. So here we end up with 1 and 538 thousandths. Easy peasy. Okay. Same thing again. If I'm looking for log of 4300ths, I'm going to get negative 367 thousandths. And then last is log of -3. Can your argument be negative? Your argument can't be negative. Okay. Reason why your argument can't be negative is remember the log function? The log function has a vertical asymptote. Do you remember our parent functions? Your log function has a vertical asymptote at x equal 0. So the log function doesn't pass over into the negative. So your argument cannot be negative. So if you have a log with a negative argument, what does that mean? Undefined, not possible, no solution, all the above. Does that make sense? So this would be not possible, whatever you want to write, no solution, but it doesn't exist. Okay. If you type it into the calculator, so if I did log of -3, it's going to tell me, oh no, non-real answer. Okay. You didn't do anything wrong. It's just it's not possible because there's that vertical asymptote, right? That says you have to stay in positive arguments only. Capiche? So, could that be a non-calculated section? I mean, because yes, a negative could be making sure you understand the rule. Yes. technically it could fall. Yes.
Can you go back to the last slide?
I will later. I can't at this very moment though. All right. So, using your answer to example 3C. So we got on 3C, that was our 1/2 negative 6 to the 64, right? It says we're going to, can you make a general statement about a log function? Not 3C. It should say 5C. Oh my gosh. Typo. This should be 5, not 3. 5C. So our general statement, in your own words, what did I just say? Summarize. What's our general statements? Think about it, because if you can put in words what I just said out loud, then that means you understand the concept. So what do we say, and why is it not possible? The argument can't be negative, and why can it not be negative? Hence, use the picture. There we go. So write it in your words. It's your words, not mine, because it's for you to make sure you understand. I said use the photo. The photo is your hint. I drew the picture. All right, so my word of choice may be different than your word of choice, correct? Because it's for me to understand. So I understand that the domain for log x is 0 to infinity because of an asymptote at x equals 0, which means that my x values have to be greater than 0. That's my general statement. So if I have an x value that is less than 0, an argument that is less than 0, then it does not exist because it doesn't fit my domain. Does that make sense? Okay. Those were my words. Your words are your words. Okay. It's for you to remember that the argument has to be greater than 0. Capiche? What? Capisco? Mhm. All right. So to make sure that we understand, we're going to go back to a non-calculator portion. This time we are using non non-common logs. And so to see that you get it, we're going to pause and see what happens as you evaluate these. So here are you're doing example number 6, A through D. So you're evaluating without a calculator, no calculator. These would be on a non-calculator part of the test. Okay. Log base 2 of 32 equals what? Log base 49 of 7 equals what? Log base 164 of 4 equals what? And log base 5, negative 25 equals what? Okay. Non-calculator. Remember that it's asking you 2 to what power is 32? 49 to what power is 7? 164 to what power is 4? 5 to what power is negative 25? That's my hint for you. Go think and be great. All right, good people. Let's see how we did. So remember, this is saying 2 to what power equals 32? That's what this is asking you. And what do we get?
5.
5, 2 to the 5th. That's 2 times 2 times 2 times 2 times 2 equals 32. Okay. On B, I remind y'all, if your base is larger than your argument, it has to be a fractional solution. So this is saying 49 to what power equals 7? What did y'all come up with? 1 over 2, you're taking the square root of 49. If you have 49 to the half, that means you're taking the square root of 49. Okay? All right. Here we have 1 over 64 to what power equals 4?
I don't think that's.
It's not 3. There's 2 things here. One, it's going to have to be a negative something because it's a fraction, right? So it's going to be a negative and it's going to have to be a fraction. Okay. So it has to be a negative and a fraction, which means that this equals negative 1 over 3. Okay. A way that you can look at this is that it's 64 to the negative power of something equals 4. Does that make sense? Instead of writing it as 1 over 64, you can write it as 64 to the negative p. That lets you know that it has to be a negative, right? And I know that it has to be a fraction because 64 is bigger than 4. Okay. So this means that the cube root of 64 is 4. So 4 times 4 times 4 equals 64. Does that make sense? Okay. All right. What happened here? Why is it no solution? What was our rule? Our arguments can't be negative. 5 to no power will ever equal negative 25. It is not possible. There's no solution, whatever you want to call it, but it doesn't work. Got it? All right. So example number 6 are ones that would be on the non-calculator. Okay. These would be non-calculated problems, which means that you would need to know the rules. Example number 7 are problems that would be on the calculator side or types of numbers that you would see on the calculator side. You would have to have a calculator. Okay. We're going to go over and remind you how to access the log base on your calculator. Okay. So if you're using a handheld, how do you get to the log base? Boom, boom, boom. You wish you had a calculator. They're just gonna it's gonna magically appear in your life. All right, so the shortcut to getting the log base is you're gonna press alpha, and I believe it's window. And you see where it says log base? So we're pressing alpha, window, and then 5. I don't know, is it 5 on y'all still? Okay, good. So we press alpha, then we press window, and then we press 5. And then now you can input whatever base you need to input. So here we have log base 3 of 15. So I put 3, then I put 15, and it gives me my approximate solution. So we have 2 and 465 thousandths. And again, it's approximation. So now we can do the next one. Again, I'm pressing alpha, window, 5. Then we're going to press 4, 58, hit enter. And we have 2 approximately, sorry, I gotta remember to write that, 9 and 29 thousandths. Okay, the next two we're gonna go and do in Desmos. You don't have to do it in Desmos, but I'm gonna do it in Desmos for the people who like Desmos. Okay, so now I'm gonna go to my Desmos. I'm gonna clear it. So to put the login, we're gonna type log, and you're gonna hit shift underscore. Okay, so you're gonna hit shift underscore, then type the base, and then arrow over. What was the number? I'm sorry. It was 0.35 hundredths. My bad. Let me do the right one. So again, all I'm typing is log, shift underscore, 0.35 hundredths, arrow over, and then type in my argument. And my argument is 8 and 4/10. I don't know. I never use it. Let's see. Go over here. Go to functions. That just seems like a lot more work. Scroll, scroll. Yep. If you scroll down, it's a little faster to just hit shift underscore. Okay. But yes, you can. But again, it's just a little faster to go shift underscore and type it in. But you do whatever makes your heart happy. I will not stop you. Okay. Again, all I'm doing is log shift underscore, and we're going to type in, is it 5/2? When you're putting in a parenthesis, I like to make sure that I put it inside of, when you're putting in fraction, I like to make sure I put in parentheses. And then again, arrow over, type in your argument. And my argument is 125. And there we go. Any questions about either input? Totally doable, right? All right. Totally doable. So we have, it was approximately -2 and 2700s, right? And then approximately 5 and 269. There we go. Questions, comments about inputting? All right, let's keep it rolling. All right, so now we're going to be talking about orders of magnitude and log models, okay? So using a calculator, we're going to compute 3 times 10 log 3 times 10 squared, such and such, okay? That is what we are going to, well, then we're going to acknowledge what is the pattern. What do you notice is happening? What is changing? And then going from there. So let's just talk about orders of magnitude. Orders of magnitude means that your argument can be written as a factor using powers of 10. Does that make sense? So when we're talking about the magnitude, we can write this as a factor using powers of 10. So this number is actually 30, but we wrote it as 3 times 10. This number is actually what? What is this number? Huh? 300, but we wrote it as 3 times 10 squared, okay? So excuse me. So that's what we're going to do. Now, when we're saying to calculate, compute, find this in the calculator, we're going to talk about what is changing here. What is the variable? Well, what is changing from this problem to that problem? What power? The power. I said the power. The power on the 10 is what's changing. So that we can get all these values, what we're doing in the calculator is we're just going to create a function model. So we're going to have y equals, and we're going to have log times 3, log of 3 times 10 to the x. That's essentially what we're evaluating. Does that make sense? Okay. We're looking for the values from, we want to find the values of our x ranging from 1 to 10. But we're not going to solve every last one. We're only going to do the ones that are here. So we're looking for x's from 1 to 10, and we're going to look at that pattern. Okay. So let me go to my handy dandy calculator. Go to Sylvie, pull her up. I'm going to just clear out my calculator. Second plus 712. Now I'm going to go to y equals, and I'm going to put in log 3 times 10 to the x. Just normal log, common log. And I'm going to go look at the table and analyze from 1 to 10 what's happening. Okay. So I'm going to hit second graph and look at my values from 1 to 10. So from 1 to 10, you can see that there's a clear pattern taking place, right? So when I looked at it, the set that created was we have 1.477, comma 2.477. And then it keeps going, going, going up to 10.477. So my integers are doing what? They're just whatever the power is. Do we see that? Whatever the power is on the 10, that is my integer. So it's just 1, comma 2, comma 3, dot, 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 all the way up to 10. And my decimal stays the same. So my decimal is, oops, sorry, The decimal is the same for every last one. It's not just a same similar rounding. It's exactly the same for each one of these. So my decimal is roughly, I'm going to write out a couple points of it. And it just keeps going and going and going. When this is taking place, when there's a clear pattern between your integers and a repetition between your decimals, that means that there is some type of magnitude taking place. So when we're looking for that magnitude, all you're doing is saying, how did it change? What was the changing factor? And the changing factor is literally paying attention to your powers. That is it. So if I say, how many orders of magnitude greater is 3 times 10 to the 10? All you're doing is looking at the powers of your base. How is that changing? So 10 minus 1 equals 9. So how many powers of magnitude greater, orders of magnitude is it? 9. That's it. It's a big word with basic math. Does that make sense? Okay. This only works when there is a clear cut of writing it as a log with a base of the same. Okay. If that pattern exists. If this pattern doesn't exist, then you can't talk about the order of magnitude. Got it? But a pattern has to exist, meaning that there's a clear pattern between the integer and then there's a obvious repetition between the decimal. All right. This is where this comes into. All of this review and tying everything together comes into us talking about real world examples. This is what this unit is really about. Is taking what you learn and applying it to problems, the real world problems. Okay. So that's why we reviewed what we've learned in Algebra 2, reviewed what we learned in last semester, added a little extra, and now it's time to apply it to the context of whatever we're doing. So first we're going to talk about comparing earthquake intensities. Okay. If you look right here, I've given you the formula. If there is a specific formula that is needed for a problem, they will give it to you on the test. Does that make sense? You do not have to have random formulas memorized. Like you would not have to have this memorized. Does that make sense? Okay. So it says here that the intensity levels I of two earthquakes measured on a seismograph can be compared by the formula log I1 over I2 equals M1 minus M2, where M is the magnitude given by the Richter scale. Okay. How many times more severe was the 2001 earthquake? Is it Yihart, India, with M of 1 equals 7.9. Then the 1999 earthquake in Athens, Greece, with M of 2, the magnitude 2 equals 5 and 9/10. Okay. So we're going to follow the rule, the formula. They gave us a formula. We use the formula. Okay. We know M1 and M2, correct? So that's where we start at. We start with what we know. We know that 7 minus 9, the 7 and 9/10 minus 5 and 9/10 equals log, but we don't know our intensity, our I sub 1, and we don't know our I sub 2, our intensity. And that's what we're going to find out. Watch how simple the math is. You're going to be like, what? That's it? All right. What's 7 and 9/10 minus 5 and 9/10? 2 equals the log of I sub 1 over I sub 2. Okay? How can you get rid of a log of base 10? Not multiply by 10. Raise it. So you're going to raise it to 10. You got to raise it to the 10. You turn it into a power. So then we end up with 10 to the 2 equals I sub 1 over I sub 2. Your magnitude is just the power of base 10. What is my power on the base 10? 2. So therefore, the earthquake I can write the earthquake in India is 100 times greater than the Greek earthquake. Earthquake. And that's because it had an order of magnitude 5. Meant 2. I said 5, and I have no clue why. Okay. The 100 comes from actually evaluating 10 squared, which is 100, right? The order of magnitude comes from what power of 10 is it? How we feel?
Where did you get 10 from?
So the formula is common log. And to get rid of common log, you have to raise it to a base of 10 because common log means that your base is 10.
That applies to whatever.
It applies to whatever the base is, yes. So if it had been log base 2, then I would have had to raise it to 2. All right. To my understanding, this would be the only type of problem that you would have to use order of magnitude, would be a Richter scale problem. Okay. Is that doable? Yes. Okay. All right. Whew. Let's keep going. Yeah, another problem. Okay, so our next problem is, well, our last problem in our notes, is comparing chemical acidity with the pH scale. So pH scale models, and again, if there is a formula that is needed that is not a common formula, it's going to be given to you. Got it? So the pH equals negative log H plus is a scale that measures how acidic or basic a substance ranks. The scale ranges from 0 to 14, where 7 represents neutral, and each whole pH value below 7 is 10 times more acidic than the next higher value. Chemistry people? Chemistry? No, no. Chemistry? Okay. No chemistry? Okay. Um, it's more chemistry. Bill, isn't this more chemistry?
Yes, it's definitely. Yeah.
I was like, this is chemistry. Yeah. If I remember very little, but I remember some of it. Balsamic vinegar has a pH of 2.4, and a box of baking soda has a pH of 8.4. What are their hydrogen ion concentrations? Okay, that H plus, that hydrogen ion is what we're looking for. Okay, brings back nightmares. Sorry. Oh yes, I'm winning. All right. So up first, we're gonna find vinegar. So we're gonna first find the hydrogen ion concentration for vinegar. So for vinegar, which is the balsamic vinegar, we know that we have 2.4 is our pH balance. Agreed? So we know that 2.4 equals negative log, and we're looking for our hydrogen ion concentration, which is that H plus. What do I need to do? What do I need to do to get the hydrogen by itself?
Oh, you do the 10 thing.
Yeah, but before I do that, what's out in front?
Yeah, negative.
I gotta do I have to do the negative first. So in order to turn this into a positive, I'm gonna have to make this into a negative. Do we see that? And now I can raise it to the 10 power.
No, I remember.
Now I can raise it to the 10 power. Okay. So now we have 10 to the negative 2 and 4 tenths equals H plus for vinegar. You don't remember doing any of this? I don't know what to say to that, but
I remember she had like a whole.
huh? Oh, okay.
She like made you like ruin like a little like you remember like a rectangle.
No bueno. But here we go. Here's my little chemistry lesson for golf for the whole year. Baking soda. So now we're gonna do baking soda. Okay, so we have baking soda And it's the same process. So we know that we have 8 and 4/10, right? So we have 8 and 4/10 equals negative log of our hydrogen. Okay. All right. So now what am I doing again? Same process, right? I have to take the negative and turn it into a, and if I change one side, I have to change the, okay. After I do that, now we're going to, now can I get close to the log? Yes, now we can get close to the log. So we have 10 to the negative 8 and 4/10 equals our hydrogen for baking soda. Okay, does anyone remember? Oh, my chemistry people, no pressure for you to remember. What are the units for your hydrogen ions?
Oh, you said units for hydrogen.
The units for the hydrogen ion. Huh? It's what? It's your molecular, your moles per liter, MOL. Do y'all remember that? It's your moles per liter. Okay. Okay. So when you go to the calculator, you type this in, it's going to give you your value. So this is what it is. So when we come over here, we type in 10 to the negative 2 and 4/10 and enter. Okay. This is not written in, we're going to write it in scientific notation. I hope some of this is ringing bells for y'all. I really do. I should not be the first one teaching it. Just like chemistry. All right, here we go. Over. I need to write this in scientific notation. So I'm going to move it 1, 2, 3 units left. So then my vinegar is what? How many moles? Moles per liter. It's going to be 3 and 98.1 times 10 to the negative 3 moles per liter. That's what vinegar is. Yes? Okay, now we're going to do it for baking soda. Perfect. 10 and negative 8 and 4/10. So for baking soda, we have 3.981 times 10 to the negative 9. And that is what our units are again, moles per liter. I can. All right, if you haven't had chemistry yet, there you go. We had a chemistry lesson. Are you looking for my objective? I didn't write it today. Oh, okay. I was like, I didn't write it today. It's written on Canvas, not on the board. You're welcome. You too. All right. Yes. All right. So then it says, how many times greater is hydrogen ion concentration of vinegar than baking soda? So we're looking for their orders of magnitude. When I'm looking and comparing how much greater it is, and the reason why I can do that is because there is a pattern that exists, right? Do y'all see the pattern? You see how they have a repeating fractions of the same, powers, all that good stuff. So there's a pattern that exists. So therefore, I can look for order of magnitude. To find the order of magnitude, simply all we're doing is subtracting, right? Essentially, but you're dividing. So we have vinegar over baking soda. Just going to write soda. Okay. And we know that that's going to be 10 to the negative 2.4 over 10 to the negative 8.4. When you're dividing, that's what you're doing. That's why we can subtract the powers. And negative 2.4 minus negative 8.4 is 10 to the 6. So vinegar is 6 orders of magnitude greater than Baking soda. Bam. How do you feel? Doable?
Doable.
Cool. All right.